Okay, this is the lecture on the notes for week one, sections 10.1 to 10.7, first part of 10.7, and the first part of 11.1. This is about exponents and polynomial operations, and a little bit on factoring. So we'll next week finish the material on factoring and then look at solving quadratic equations. But this week, just some basics from chapter 10 and a little bit of chapter 11. All right, so you see the basics of exponents here, section 10.1, and the concept of an exponent. So if you have a to the nth power, you know that means take a, the base number, and multiply by itself whatever n is. So if it was a to the third power, that means a times a times a. If it was a to the 10th power, you'd multiply 10 a's together. It does not mean multiplying by n. You're never multiplying by the exponent. When you're evaluating a to the nth power. You just multiply by a bunch of a's, or whatever the number is. Now, if you have negative a to the nth power, that means what's right before the exponent? The parentheses. So you would take that whole parentheses, negative a, and multiply by negative a n times. So if it was negative a in parentheses to the fifth power, then you'd go negative a times negative a times negative a times negative a times negative a, 5 times. However, this is where students get a little bit confused sometimes. If you don't have parentheses and all you have is a negative sign out in front of it, then that negative sign is just saying, give me the opposite of a to the nth power. So the thing that is right before the exponent is just the letter a, not the negative sign also. So you'll only do the a n times and only have one negative sign. Because the negative sign, just like with negative x, could be thought of as negative 1 times x. It could be thought of as a negative 1. So it's really negative 1 and then times a, whatever n times you're going to multiply a by. So, because you always do exponents before you do multiplication, and the negative 1 is really like out in front is multiplied. Now, that uses the principle that an exponent only applies to the item right before the number, or right before the exponent. So 6 to the third power would mean 6 times 6 times 6, or I think it's 216. Okay, I think I can draw here and go 6 times 6 times 6, and I believe this is 216. All right. In the next example, you have negative 2 to the fourth power, and the negative 2 is inside parentheses, so we're going to take negative 2 and multiply by negative 2 4 times. Now you can put negative 2 in parentheses if you want every time, but you basically have to, because right before the exponent is the parentheses, we're going to take everything in the parentheses 4 times. So if you multiply that out, of course, 4 negatives would make a positive. An even number of negatives makes a positive. So we'd end up with positive 16. All right. Now in the next example, you see that we have just the opposite of 2 to the fourth. In other words, it's not negative 2 taken to the fourth power. That's what you'd have if you had it in parentheses. It's just a negative 1 in front, and then times 2 multiplied 4 times. Okay, so of course 2 4 times gives you 16, and then times negative 1, so this is negative 16. Okay, so you can see that it's a different. And if you if you don't believe me, you can try it on the calculator. If you put negative 2 in parentheses, it'll give you positive 16. If you don't put the negative sign in parentheses, just have negative of 2 to the 4th, it'll give you negative 16. All right? And then in the next example, the negative sign out in front there is treated like a negative 1 again, but this time you have parentheses, so you have negative 2 multiplied 4 times, and of course you have a total of 5 negatives. So 5 negatives would end up negative, so this time you do get negative 16. All right, again. And don't, you wouldn't multiply, you wouldn't think, okay, I got a 2 negatives makes a positive, because the exponent has to be done first. And the exponent tells you to make 4 of them, and so that gives you a total of 5, which overall makes it negative. You get the drawing tool again. So the exponent applies only to the 3. So the 5 will only do 1 time, but we'll have 3 3's multiplied together. All right. So if you multiply 5, now you can just multiply everything together. 5 times 3 is 15. 15 times another 3 is 45. 45 times another 3 is 135. So 135 is going to be your answer there. All right. Now in the next example, it's an expression with x. Find 7x to the 3rd power when x is negative 2. So we know the value of x, it's negative 2, and we're going to insert that into the expression where the x is. So we have 7 times negative 2 to the 3rd power. So because the negative 2 is in the parentheses and the parentheses is taken to the power, we're going to have just 7, but then 3 negative 2's. Okay, so how many negatives do we have? Well, you can see we have 3 negatives, so overall it's going to be a negative. And then if you multiply 2 times 2 times 2, that gives you 8. And then 8 times 7 is 56. So the answer is negative 56. All right. So now we're going to look at some exponent laws, and I'll try to explain why these exponent laws work. What makes them true? Okay. And we'll look at some examples. So the first one, we have a to the mth times a to the nth power equals a to the m plus n. So in other words, when you have two things with the same base, you can combine them by adding the exponents into one exponential expression by just adding the exponents. So here's an example. If you have 3 to the 2nd power times 3 to the 5th power, it would be 3 to the 7th power. So why is that? Well, 3 to the 2nd power really means 3 times 3, right? And then 3 to the 5th power means I'm going to multiply 5 3's together. Let me put a dot in between each of them. Okay. And then what's the operation in between these two things? It's multiplication. So you multiply them together, and so basically you have a total of 7 3's. So that explains why it would be just 3 to the 7th power. All right. So when you multiply two things with the same base, you're going to add your exponents to combine it into one exponential expression. Now here, this has some numbers out in front in addition to the x's. So those you're just going to multiply like normal. 5 times 3 is 15, okay? And then you have x squared times x to the 4th. So you can add the exponent and say x to the power of 2 plus 4, or 6, okay? Now one of the mistakes I see some students make is they write 15 to the 6th power and they lose the x. But you have to keep the base. The base is x. All right, the next problem is a distributing problem. because you've got a monomial, a single term, times a binomial, two terms. And so we're going to basically distribute to the first term. So multiply 2y to the third times the first term. So 2 times 7 is 14. And then y to the third times y to the second would be y to the fifth. Okay? And then you have to go 2y to the third times negative 4. So 2 times negative 4 is negative 8. So just put minus 8. And then you have y to the third. Now, you don't have any y's to make this exponent any larger, but that's the expression. Now, of course, you cannot combine these terms because you're subtracting, and you cannot subtract terms unless they're like terms. So hopefully you remember that. All right, in the next example down here, in the next rule, so that was called the product rule, where you're adding the exponents, but it's because you're multiplying a product of two things with the same base. You can add the exponents. The next is called the power rule, but I sometimes call it the power to a power rule, because we're taking a power to another power. So the rule is over here, and it says, if you have a to the nth power, so you have a power, and you're going to take that to another power. So you got to have parentheses with another exponent on the outside. And so the answer, or the simplified version of this, is a to the power of n times m. So in other words, when you have a power to a power, you can multiply your exponents. All right? So why is that? So let's consider this example, and I'll talk about the y in a minute. So if you have x to the fifth to the power of 3, you have a power to a power, so I can write my base to the product of 5 and 3, so x to the 15th power. All right? So the reason why that works, well, think about, okay, the exponent on the outside is this 3. So this means take the parentheses to the third power. So that means I'm going to take x to the fifth times x to the fifth times another x to the fifth. All right? Well, the previous rule up here, the product rule, said that when you have things multiplied together with the same base, you can add the exponents. So that's the next step. I have x to the 5 plus 5 plus 5. We just added all the exponents. And of course, that equals x to the 15th power. So you can see why this works. It's basically because a shortcut to addition is multiplication. If we have 3x to the fifths multiplied together, we're just going to add 5 plus 5 plus 5, but the easiest way to do that is just 3 times 5. All right? So that explains that rule. Now the next example or rule is called the power of a product rule. Now this is where I have a product of two things. So inside the parentheses here, AB, that means A times B, so that's a product, taken to a power, so power of a product. And so basically it just means that you can take each item inside there to that power. So A to the nth power and B to the nth power. All right? And the reason for this, well, think about this. Suppose you have AB to the nth power. What does that mean? Well, if you have nth power, that means I'm going to multiply AB times AB times AB n times. However, whatever n is, I'm going to multiply AB times itself n times. Okay? Well, if you just rearrange the term, this is all multiplication. So if you just rearrange the terms and put all your A's first and all your B's second, then think about, okay, well, how many am I going to have of each? Well, I'm going to have n of A's, and I'm going to have n of B's. So this is just A to the nth and B to the nth. So you see why AB to the power of n must equal A to the nth, B to the nth. All right? And so to see this in action, we can take something like this monomial, 3x to the second power to the fourth power. So do you see that we have two things multiplied together inside there? 3 times x to the second. So you got the number 3, and you have the number x squared. And you're going to take each of those to the fourth power. So that's what I did. 3 to the fourth, and then x squared to the fourth power. Well, what is 3 to the fourth? Well, 3 times 3 times 3 times 3 is 81. Okay, so I'm going to write down 81. And then what do I do when I have a power to another power? Well, that's up here, the power rule. I'm just going to multiply the exponents. So it's going to be x to the 8th power. Okay, now do you need to write that dot? No, you could just write 81 x to the 8th power. Now I, of course, wouldn't take off if you did write that dot, but it's just a little bit more compact if you write 81 x to the 8th power. All right, so let me move this up further. Another example here. Get my drawing tool back. All right, so another example here is this monomial. I've got this monomial here, and I'm taking it to the third power. So that really is three things multiplied together, -5, x, and y squared. So basically, I'm going to take -5, all right, and I'm going to take that to the third power, and I'm going to take x to the third power, and then I'm going to take y squared to the third power. So let me write y squared inside the parentheses, okay? So now you might not even have to do this middle step. You might be able to do everything in your head, but just, you know, if you need to show your work, show your work. If you don't need to, fine. Now, in the homework, I would expect to see some work because even I, after 30-some years of teaching math and doing math problems, I can't do everything in my head either. So, you know, I would expect that some of the work you'd be doing in you need some scratch work for it. So I'd like you to show that work and then, you know, send that to me or post it. Okay, so if you have -5 to the third power, -5 times -5 times -5, that would be -125. And then you have x to the third, so I'm going to write x to the third. And then I have y squared to the third power. So when you have a power to a power, you're going to multiply your exponents. So you get y to the 6th. So -125, x to the third, y to the 6th. All right. So we've looked at three different laws now. The product rule, the power rule, and the power of a product rule. Now let's look at the power of a quotient rule. All right. So you have a quotient. A quotient is a division problem, like a fraction. So a over b to the nth power, well, it just basically says that you can take the top to that power and the bottom to that power. So a to the nth over b to the nth. So you basically can take the top and the bottom separately to that power. So in the example here, you have 2x to the 5th to the third power, or 2x to the 5th over -3, all to the third power. But I'm basically going to take the things in the top to the third, so 2 to the third, first of all, and then x to the 5th to the third. So I'm going to go ahead and put that in parentheses. Take x to the 5th to the third power, and then -3 to the third power. I hope you'll forgive my handwriting. It's not easy writing with the mouse. But then you can take 2 to the third power, and that gives you 8. And then when you have x to the 5th taken to the third power, that would be, well, you have a power to a power. You can multiply the exponents, so that's to the 15th power. And then you have -3 to the third power. Well, -3 times -3 times -3, that would give you -27. Now, I would prefer if you do not leave a negative in the bottom. So if we multiply top and bottom by -1, that'll change this to -8 x to the 15th over 20. See, I can't erase that. Okay, I erased everything. Okay, but what we had there was 8x to the 15th over 27, but we put the negative sign on the top instead. All right, so that's all we had to do is, I wouldn't leave a negative in the bottom. There's a reason for it later that we'll talk about, but it's just not usually done. Okay, so the next rule is called the quotient rule, and you could say it's when you have a quotient of two things that have exponents but with the same base. So the same base, and you have a quotient. So like here we have a to the mth power over a to the nth power, so they both have the same base of a. The rule says that we can write that as a single exponent, as in a to the m minus n. So you can subtract the exponents. Now if you remember, we had a product rule where you added the exponents, and since the opposite of multiplication is division, so instead of adding the exponents, we're going to subtract the exponents. So here's an example. X to the 7th over x to the 3rd power equals x to the 4th power, because you can subtract the exponents. Now, the reason that works is because you basically are going to cancel. So you have x to the 7th over x to the 3rd, and you could write x to the 7th as 7 x's multiplied together. The x to the 3rd would be 3 of them. And how many would cancel? Well, 1, 2, 3 will cancel. And that leaves 4 remaining on top. And so it's x to the 4th power. Okay? So that explains why you can subtract the exponents. What you're really doing is just canceling the exponents on the bottom. All right, now if it was flipped over, if you had x to the 3rd over x to the 7th, the extra ones would end up on the bottom, so it'd be 1 over x to the 4th, because you're just canceling 3 of the x's, and you have the extra ones left over on the bottom. Now, the next rule is kind of strange for some students. It says that a number a, or any number to the 0 power, equals 1. It doesn't equal 0, it equals 1. So any number to the 0 exponent will equal 1. Now if you think about this, a to the 3rd over a to the 3rd, of course that's going to equal 1, because anything divided by itself will equal 1. But according to the quotient rule, we could subtract the exponent. So a to the 3rd over a to the 3rd would be a to the 3 minus 3, or a to the 0 power. So both of these started with the same expression, so it must be that a to the 0 must equal the same thing that, we got on the first time. So it should be that a to the 0 equals 1. So that means anything to the 0 power equals 1. So over here, I have this whole parentheses taken to the 0 power. And so since everything is inside the parentheses taken to the 0 power, that will equal 1. It doesn't even matter what x is, because everything's in parentheses taken to the 0 power, the whole thing will equal 1. Now there's more examples on page 813. There's also some in the homework that are a little tricky, like for example, if it said 5 and then in parentheses it had something like 3x to the 3rd y, all that to the 0. Now even though you have a 0 power, the answer is not 1. because the 5 is not to that power. Only the parentheses is that to that power. The 5 stays the same, but all this in parentheses taken to the 0 power, that would equal 1. So your final answer is 5, not just 1. All right? All right, so then what do you do with a negative exponent? So how do we handle negative exponents? We talked about 0 exponents. That equals 1. But negative exponents, what do you do? Well, according to this rule, if you have a negative exponent, you can say 1 over that base to the positive exponent. 1 over that base to the positive exponent. So if you look down here, you have 10 to the negative 2 power. We can flip it over, like the rule says, 1 over the base to the power. So it'd be 1 over 10 to the positive 2 power. Well, 10 to the positive 2 power equals 100. So we basically have 1 over 100. Now, if you try this on your calculator, 10 to the negative 2 power, if you know how to take something to the power, you're going to get, the calculator will eventually say 0.01, because 1 over 100 is 0.01. So you could try that on your calculator. Now, the reason the rule works can be seen if you look at this example. So if you have a to the third over a to the fifth, you know, according to the quotient rule, the one at the top of the page that we just talked about, you can subtract exponents. So 3 minus 5 gives you a to the negative 2. However, let's say you do it a different way. You have a to the third over a to the fifth, and you write it out. So a times a times a, and on the bottom you have 5 a's. Well, there's some a's that cancel, and you end up with 1 over a times a, or 1 over a squared. Now we started with the same thing, a to the third over a to the fifth, and doing it this way with the quotient rule, we got a to the negative 2, but doing this way with cancellation, we got this. So doesn't that show that a to the negative 2 power would equal 1 over a to the positive 2 power? Which is exactly what the rule over here is saying. You can flip it over and change it to the positive power. In this last example, you have negative 2 to the negative 4th power. So whenever you have a negative exponent, we're going to flip it over. So 1 over negative 2, and then take it to the positive 4 power. Well, negative 2 to the positive 4, you're going to be multiplying negative 2 times itself 4 times, and you end up with positive 16. But that would be on the bottom. So 1 over 16. All right? In order to let you see the concept a little bit better, you could look at this example. And so what is 10 to the third power? Well, clearly 10 to the third power is 1,000. Okay, so let me get my tool out. 10 to the third power is 1,000, so I'm going to write 1,000. 10 to the second power is 100. 10 to the first power is just 10. Now, we're going down in powers, 3, 2, 1, 0. But what would the pattern suggest the next number should be? Well, we're dividing by 10 every time. 1,000 divided by 10 is 100. 100 divided by 10 is 10. So if we're decreasing by 1 here, we should continue the same pattern. And if you divide 10 by 10, you get 1. So that shows that 10 to the 0 power must equal 1. Now, if you have 10 to the negative 1 power, well, you're just continuing the same pattern. If you divide 1 by 10, you get 1 over 10. Okay? Which, that's what you'd get if you use the rule for negative exponent. You'd flip it over, say 1 over 10 to the positive 1 power, which would be 1 over 10. And then if you divide 1/10 by 10 again, it would be 1 over 100, which is 1 over 10 squared. So that shows the negative exponent rule, that you flip it over and make it 1 over 10 to the positive 2 power, which is 1 over 100. And then, of course, if you divide by 10 again, if you have 100th of something and you divide by 10, that equals 1 over 1,000. And 1 over 1,000, of course, is the same as 1 over 10 to the third power. And so, of course, if you have 10 to the negative 3, according to the negative exponent rule, it's 1 over 10 to the positive 3. All right? Now, this next example talks about what do you do with if you have fractions. And over here, rule for fraction, if you have a fraction to a negative exponent, you just flip the fraction. You don't have to do the 1 over thing. You just flip the fraction and change it to a positive exponent. So over here, I actually did the 1 over thing, but I wanted to basically show you that it's basically flipping the fraction. So if you have 2/3 to the negative 1 power, you can use the quotient rule, flip it over, negative exponent rule, flip it over, and you'd have 1 over 2/3 to the positive 1 power, which is, of course, 1 over 2/3. But then if you multiply top and bottom by 3, you get 3 over, and then these 3's here cancel. So basically 3 over 2. So the answer is basically the reciprocal of the original 2/3 that we had. All right. Now, the next example is about as tricky as it'll ever get with exponent laws. If you can do this example, you should be doing okay. So I've got this fraction to the negative 2 power. So the first thing I'm going to do is when I have a fraction with a negative exponent, I'm going to flip that over and change it to the positive power. So I'm going to go y over 3x squared. And that's changed to the positive 2 power. Then I'm just going to recopy what's in the next parentheses, 2x over y squared. If I can write this. All right, that's y squared, in case you can't read it. So now I've handled the negative exponent. Now I want to square everything on the top and the bottom, and on the second fraction, take everything to the third power. So y to the second power would be what I'd end up with on the top. And I'm going to go 3 to the second power, which is 9. And then x to the second power, taken to the second power, well, you multiply the exponents, 2 times 2, and you get 4. Okay? And then on with the second fraction, we're going to take 2 to the third power, and you get 8. X to the third power over, and then we'll go y squared to the third power. That would be y to the 6th power. All right. Now, at this point, there's a couple different ways you could do this. We could just, I'm going to try to change the color to blue, I guess. All right, so I'm going to do some cancellation. So I see that I've got 3 x's on top and 4 x's on bottom. So I can cancel those 3 x's and cancel 3 of these 4. And so that'll leave with an exponent of 1 on the bottom. Then the y squared, I've got 2 y's here that will cancel with 2 of these y's. So that 6 will drop down to a 4. So the only thing left up top is the number 8. And so I actually did this without rewriting it, but it's basically going to give you the answer of 8 over 9 x to the first power, so I can just write x, and then y to the 4th power. So 8 over 9x y to the 4th. All right, so you can see that that was a bit tricky, but we just reduced the fraction. All right. And then one of the applications to negative exponents is scientific notation. So scientific notation must use the form, the only form you use for scientific notation is this a decimal number between 1 and 10 times 10 to some power. So you always have to have some decimal number times 10 to some power. All right. Now the power is a non-zero integer. We would never use 10 to the 0 because 10 to the 0 is just 1, and the decimal times 1, you could just write the decimal the way it is. So we're going to have some positive or negative integer for n. All right, but don't forget the 10 in there. It's necessary. So here is an example, 32,500,000. So you ask yourself, first of all, where would I place the decimal point to make this number a number between 1 and 10? So you'd place it here after the 3. So that's what I did over here. So I've got my decimal number. So this is my decimal number. And then times a million, or I'm sorry, 10 million. And then you got to write it with the exponent. So 10 to the 7th power, because if I move the decimal place over 7 spaces, it gives me 1. So it would be the decimal number 3.25 times 10 to the 7th power. Now you can see the 7 spaces right here. I moved it over 3 places and another 3 and then another 1 space. So a total of 7 spaces there. So 3.25 times 10 to the 7th power. Now if you have a small number like 0.00047, you still ask yourself, where would I place the decimal point to make it a number between 1 and 10? And so it would be here between the 4 and the 7. And then I have to move that over 1, 2, 3, 4 spaces to get there. Now this is just another way to do it with this decimal number 0.0001, but you could just count how many spaces. And then the answer is 4.7 times 10 to the negative 4th power. Now that's because this number is 10 to the negative 4th power, this decimal here. But another way to do this is just remember, if you have a small number, then you should have a negative exponent. And we started with a small number on that example, so we're going to have a negative exponent. If you start with a large number, as in the first example, you're going to have a positive exponent. I think those rules are a lot better to remember than rules that talk about whether you move it to the left or the right and positive, negative, and all that. It gets confusing because sometimes you're going one way and sometimes you're going the other way, and the rules are not consistent. So these rules will stay consistent. If the number is a large number, then you're going to use a positive exponent. If the number is a small number, then negative exponent. Okay, so here you've got a positive exponent, so you're going to end up with a large number. So what you do is you write 8.2, and then you move the decimal place over 5 spaces. So we would have moved it over 5 spaces, and it would be right there. And so it's the number 820,000. The next problem, 8.2 times 10 to the negative 5. You're going to move it over 5 spaces, but you're going to move it over to the left because that would make it a smaller number. So from where it was moved over 5 spaces, 1, 2, 3, 4, 5, you end up with 0.0000820. Now, I want you to notice I kept the 0, this 0 right there. I kept that 0 in my final answer, the 0 after the 2. And the reason I did is because the scientist or whoever wrote this number down would not have written that 0 if it wasn't a significant digit, meaning something that he measured. So don't lose precision. Keep that 0 for precision, all right? Now, in the previous example, excuse me, you have that 0 right after the 2, so that means that the number is going to be precise to the nearest 1,000. This 0 right after the 2 it's measured to the nearest 1,000. So that's one good thing about scientific notation numbers, is that you can know how precise the number is. All right. Now, so we talked about exponents and exponent laws and negative exponents and all that. Now we're going to look at polynomials and polynomial operations. Okay, so polynomials have terms, and terms are always separated by plus or minus signs. That's how you can tell how many terms there are. So if you see two expressions with a plus or a minus sign in between them, then there's two terms for that polynomial. A term is a number, or the product of a number and a variable. Even if you had just x, that's a term, because you could write it as 1 times x, 1x. But usually it's something like 5x squared or 7x, or it could be just a single number like 2. That's a term. Now, the coefficient of a term is the number in front of the term. Then we can classify terms by, or excuse me, classify a polynomial by the number of terms it has. So if it has just one term, it's a monomial. If it has 2 terms, it's a binomial. If it has 3 terms, it's a trinomial. And then after that, we just say 4-term polynomial, 5-term polynomial, etc. But that's how you can classify polynomials. So the next important thing about polynomials is the degree of the polynomial. And first, though, we have to talk about the degree of a single term. So the basic thing for the degree of a term is how many variables does it have multiplied together. So if you look at the expression negative 3x to the 5th power, that term, because we could write that as negative 3 times x times x times x times x times x, in other words, 5 variables, 5 x's multiplied together, so the degree is 5. Okay, now with the term 4x squared y, that degree is 3, because that means 4 times x times y. And so how many unknowns, how many variables do we have multiplied together? We have a total of 3. We got 2 x's and 1 y. So it's a degree 3. All right? So that's the degree of a term, of a single term. But what if you have a whole polynomial, like this long polynomial right here? 7x to the 4th minus 3x to the 3rd plus x squared minus 4x plus 1. Well, you don't add up the x's. You just take whatever's the highest term in terms of degree. Because that's the dominating term. The term that's the highest degree, that dictates or determines the characteristics of that polynomial. We'll study some of those characteristics later. But you just go by whichever's the highest. So because the first term, 7x to the 4th, has the highest degree, its degree is 4, then the degree of the whole thing is 4. All right? Now, like terms can be discussed in reference to a polynomial. Like terms are terms that have the same variables and the same powers on those variables. So in this expression, I have 6x to the second power, and I also have a 5x to the second power, 5x squared. And so we could add those together, and that would be 11x squared. Excuse my handwriting again. And then we also have negative 1x. You put a 1 in front of that there. And 4x, which adds up to 3x. Oops. All right. And then we have the minus 7, which doesn't have anything we can add to it. But that's the answer when you combine like terms. Now the next example is another skill about polynomials, evaluating a polynomial. The word value, a root word is inside of that word evaluating, because we're going to find the value of that expression, that polynomial, if x equals the known value negative 1. We're supposing we know what x is. So we're just plugging in. We're just plugging in negative 1 into that expression. And so I did already. You see I plugged in negative 1 here as well as here, because x occurs twice in the expression. So wherever x occurs, you're going to plug in that value. And then negative 1 to the 5th power is negative 1. Times 3 would be negative 3. And then here we have negative 1 squared. You got to do the exponent first. That's positive 1. And then negative 2 times positive 1 would be negative 2. So we have negative 3 and negative 2, or negative 3 minus 2, and we get negative 5. So just, plug in and evaluate using the order of operations. Now with adding and subtracting polynomials, we're basically, with addition anyway, we're just adding like terms. So again, we're going to look for the terms that are like terms that have the same variable and the same exponent on the variables. So I have 2x squared and x squared, and that is 3x squared. And then we have negative 1x and 5x, and that gives you 4x. Okay, let me get this written. And then we have the minus 1. And so that's the answer. Now, one way you could have done this is over here, where I talk about how you can line up the terms vertically. So you put your x squared terms in one column, and you put your x to the first power terms in another column, and then you put your numbers in, and then you just add downward. So you get the same answer, of course, but it's just a way of organizing the terms. So the next thing we're going to look at is subtraction. And subtraction could be thought of as adding the opposite. You can treat it as if it's the first polynomial plus the negative or the opposite of the second polynomial. That's because a minus b is the same as a plus negative b. So what we're going to do is distribute the minus sign in the second parentheses to all the terms. So like, for example, if we have this polynomial minus a second polynomial, we can write it as plus the negative. You see right here where we wrote it as the first polynomial plus the negative of the second polynomial. And then we're going to just distribute that negative sign, which you can treat like a negative 1. But we're going to distribute that negative sign to all three terms, or all the terms in the second parentheses. So that'll become negative x squared, positive 2x, and negative 7, as I have over here. So now it's changed into an addition problem. So we'll add 4x squared and negative 1x squared, which would be 3x squared. And we have negative x plus 2x would be positive 1x. And then we have 9 minus 7, which would give us 2. So make sure that you distribute that negative sign. A lot of students don't get this correct, even though it's just subtraction, so it shouldn't be difficult. All right, so in the next example, you distribute the minus sign, like I said before, and so we're treating it like a negative 1 that's getting multiplied by every term in the second parentheses. And so that gives you these terms. You have a negative 3x and a minus 7x squared and a positive xy squared. Okay, now the negative xy squared and the positive xy squared, they're going to add up to 0, of course. Negative 1 and a positive 1 add up to 0. So with these terms, and so they'll basically disappear. And then you have the 4x squared minus 7x squared, and that gives you negative 3x squared. And then you have the minus 3x at the end. So that's the answer there. Now, some students think they have to factor this or go any further. No, you don't. You cannot combine these terms, of course, and I didn't ask you to factor the polynomial, so distributing out a 3x or anything like that is not what was asked. You just have to do the subtraction and combine your like terms. All right?